Good morning. In the previous classes, we have already discussed about the nature of entropy for a specific type of cycle. Okay, that means we have proved the first point, which is the cyclic integration of ds is equal to 0 for a specific cycle. Okay, and we used Carnot cycle to prove this point. Okay, so the first point is done. That means entropy is a state function for a cycle. Okay, so in this video we're going to prove the remaining 2 points, which are the cyclic integration of ds is equal to 0. That means the entropy is a state function for your any substance. Okay, and third one is your entropy is a state function for any cycle. So if we can prove this remaining two, that then we can say that the first one, second one, and third one is correct. That means the entropy is a state function for the every substance, macroscopic substance present in this universe. That means we can use this concept in thermodynamics. That means we can say that the entropy is a state function, okay, for all the system and surroundings. Okay, so let us discuss the point number 2. Okay, that means the entropy is a state function for any substance. Okay, so let us discuss this one first, and then after this one we're going to move to the third one. Okay, so this point, actually the second is what the integration of cyclic integration of ds is equal to 0 for any substances. Okay, so to prove this one we're going to use the concept of mainly efficiency of some machine. Okay, so the basic idea or basic concept behind the use of this and this efficiency term is that, let us consider, actually the concept behind is that if a machine, let's suppose machine A, this is a machine, okay, and here a machine B. So let's suppose we are taking two machines, okay, two different machine which are made of different substances. Okay, so this point is important. They are made of different substances. Okay, and if we put these two machine in between two specific source and sink, okay, having some amount of temperature, okay, a fixed amount of temperature. So that means the TH, that means we put this machine in between the TH and TC, and also we put this machine in between the TH and TC. That means the conditions are same. That means the temperature difference for these two are same. Okay, and if supposed the change of this this absorbance, or let's suppose the QH, that means the amount of heat absorbed by this A is QH. Okay, so and also it will going to, let's suppose this will going to absorb some amount of heat, and it will going to convert this heat into some works or some the remaining part will be your it will going to remove it the remaining part of the heat energy into that sink or source. Okay, so the main concept is that if we put any machine inside this two temperature gradient, okay, so if we try to calculate their efficiency, then the efficiency must be equal to each other. Okay, that means the efficiency of A and efficiency of B should be equal. Okay, always equal. So if the efficiency is equal, that means the efficiency will going to related to the what? Related to the temperature and the difference of the heat. That means the change of the heat. Okay, that means that this efficiency will going to relate or will going to depends on temperature and the dq. Okay, so that means again we know that the entropy is related to T and dq. Okay, so we know that entropy for reversible process is equal to dq reversible by T. Okay, so that means if the efficiency of the machine which are put in between two temperatures, same temperatures, okay, then uh, the efficiency of the machine A is equal to the efficiency of the machine B. Okay, so that means the entropy change B also for the machine A is equal to the machine B. Okay, so the meaning is that the any again we already considered that the machine A and machine B is composed of different material or different substance. Okay, so that means the change of entropy is not depend upon the materials or the substance which are used to prepare these two machines, because the entropy change is same. Okay, the change of this part and the entropy change of this part, total change of entropy will be same regardless of their the substance which are used to prepare this to machine. Okay, so this is the basic concept which we will going to used. Okay, uh, which we will going to used to prove that the entropy is a state function. Okay, clear? So before calculating the entropy, we're going to calculate the or we're going to use the terms efficiency, because once we have the idea about the efficiency, that means if the efficiency of these two, if once we can prove that the efficiency of this A and efficiency of this B is equal, then we can say that if the efficiency of A and efficiency of B is equal, then we can say that the change of the entropy for this system and for for this machine or and for this machine is also same. Okay, so we can say that the entropy is a state function regardless of the material which is used to prepare those machines. Okay, so let us discuss in details. Okay, so first what we have to do, we have to prove that the efficiencies of these two machines are same. Okay, so for that we have to know about the efficiency. What is efficiency actually, and what is the definition of efficiency before calculating the efficiency of this one and this one. Okay, so let us discuss about the efficiency. Okay, so actually the efficiency is related or defined mathematically is actually efficiency is this is symbolized by E. Okay, and in some book it will be you may find this symbol also. Okay, but in this book actually I have taken these images from Atkins. Okay, so in that book the efficiency is expressed by using this epsilon. Okay, so epsilon is equal to the work performed divided by heat absorbed. Okay, so it is actually the efficiency of a machine or an engine can be defined as this mathematical formula. That means the work done by that machine by absorbing some amount of heat. Okay, so how much work is able to gain from that machine by absorbing some specific amount of heat is actually the efficiency of that machine. Okay, so we can say that mathematically you can write that the work can be represented by W, and since we are talking about the work performed, that means we are talking about the amount of work, no? So we have to use the magnitude of that work. And let's suppose the absorbed heat is QH. Okay, so QH. So this is the definition of efficiency of any machine, okay, or any engine. So if you go to that PDF file given in this presentation, and here if you're going to see the figure 3.7, then here the structure or the image is like this. Okay, so I am trying to draw this one. So let's suppose this is your source. Okay, this is your source whose temperature is higher than the sink. Let's suppose this is your sink. This is cold, this is hot. Okay, then this one. So let's suppose the temperature of this excuse me, this source is TH, and the temperature of the sink is TC. Okay, so suppose we are taking a machine, and we are put this machine inside these two source and sink. Okay, so that means this machine, let's suppose this machine can absorb some amount of heat from that source, and let's suppose the amount of heat is QH, which is absorbed by this machine. Okay, so we know that by the second law of thermodynamics, the machine, we cannot prepare or we cannot make a machine which can have 100% efficiency. That means the machine, and no machine can convert it the amount of heat which is absorbed by it into totally in the work. Okay, so it will going to lose some energy in form of heat. Okay, so let's suppose it will going to give some work. Okay, it will going to do some work, and the amount of work is represented by W. Okay, and it will going to release the amount of heat, let's suppose QC amount of heat, which cannot be converted into the work. That means the remaining part. Okay, so in this example, they said that the amount of QS is equal to 20 kilojoule. Okay, and here the 15 kilojoule, they said that it is your minus 15, which is always remember that this is negative. Okay, it is less than 0. Okay, so that means the efficiency for this example will be W, that means this amount of work, divided by that is the amount of heat, which is absorbed. So here if you notice carefully, then you see the QH amount of heat is absorbed by this machine. Okay, and it will going to QC amount of energy cannot be converted into W. That means the loss of, that means how much energy, that means how much heat will going to convert it into work. So that means the work will be the QH, okay, minus QC. Actually this is, let's suppose it is plus, okay, minus QC. So in these books actually it is written like the work is equal to QH plus QC, but here they taking that QC is in form of negative. Okay, because this is your, actually they said that in this book W is equal to QH plus QC. Okay, and they consider that QC is less than 0. Okay, but you can even also use this one. Okay, but here in this case what we're going to what is the concept? The concept is that the work is the remaining part of the QH. Okay, that means that this amount of energy or heat will going to be absorbed by that machine. Okay, and this amount of heat will be released by that machine. That means this amount of heat cannot be converted into their work. Okay, so the amount of work will be this one minus this one. Okay, understand? So similarly, this one also, the total work will be what? The QH plus QC, but here it is less than 0, so it will be negative. Okay, so if you use this procedure or this procedure, the result will be the same. Okay, so here the W is equal to your 20 kilojoule plus, but here since it will be your minus 15 kilojoule, so 5 kilojoule. And if here if you use this one also 20 kilojoule, direct minus 15 kilojoule, so 5 kilojoule, same thing. Okay, but here in this part they used QC is less than 0 because it is absorbing and it is releasing. Okay, that means this is defined process. Now this is absorbing process, so it is plus, but this is your releasing process. That means this part of heat is going to release by this energy, this machine to that sink. Okay, so this is represented by negative, that means less than 0. So okay, this is gain, this is loss. Okay, so different thing now, so plus minus. So this is because of this minus is coming from that concept. Okay, so we can calculate the efficiency of any engine by knowing that amount of heat, how much heat will going to absorb by the system, and how much heat is going to release by the system during that process. Okay, so that means we able to know that epsilon is equal to QH plus QC divided by QH. Okay, so this is the concept. So what we can now write, we can write that 1 plus QC by QH E. Okay, so again we have some idea about this second terms, which is QC by QH from the previous study. That means the first point actually, in which we use actually we have already proved in the justification part that QC by TC, actually this is minus na, QH by TH. So we have already proved this one in the justification part that in that previous video. Okay, so if you don't understand this point, then you can go to that video and you can check this one. Okay, so we have this value QH by TH is equal to QC by TC, but here one negative sign is there, no? So from this relation, what we can write? We can write that QC by QH is equal to minus TC by TH. Okay, so just cross multiplication. Okay, simple mathematics. So we can replace this value from this equation, this value by this one. Okay, so here we can write 1 minus TC by TH. So efficiency is equal to this one. Okay, so you can write here or. Okay, so efficiency is equal to, that means 1 minus TC by TH. So this is the mathematical formula of efficiency, which can be used to calculate the efficiency of any engine. Okay, so we have some ideas. So you see here the efficiency is related to the temperature of the sink and the temperature of the source, and also we can say that efficiency is related to the amount of heat which is absorbed by that machine, and the amount of heat which cannot be converted into their work. Okay, so this is the amount of heat which cannot be converted into a work. Okay, and this is the heat which is absorbed by the system. So that means efficiency is related to the Q, that means the change of heat, and also the temperature. So we have this idea of that that efficiency and the definition of efficiency and the mathematical expression of the efficiency. Okay, so now we have the efficiency. So we can now use that this concept of efficiency in to actually prove the second point, which is the cyclic integration of ds is equal to 0. That means the entropy is a state function for any substance. Okay, now we are going to prove second point, that is the entropy is a state functions for any substance. Okay, by using the concept of your efficiency. Okay, for that, suppose we have one hot source having temperature Th and one cold sink having temperature Tc. Okay, and suppose we are taking two machine A and B which are made of different substances. Okay, that means let's suppose the substance which are used to prepare the machine A is Sa, and the substance which are used to prepare the machine B is Sb. Okay, and as A is not equal to Sb, that means the substance are different. Okay, and they may be any substance, that means arbitrary substance. And again, let us consider that the efficiency of the machine A is Ea epsilon A, and the machine B is epsilon B. Okay, so here actually to prove that entropy is a state function, we have to prove that the efficiency of A is equal to the efficiency of B if we put that two machine in the same source and same sink. Okay, so that is our main aim. So if we can prove this point, that means the efficiency of this one is equal to the efficiency of B, regardless of the substance which are used to prepare these two machine, then we can say that the entropy is a state function. Okay, so for this one we can actually indirectly actually we can indirectly prove this concept. That means the entropy of this A is always equal to the entropy of B by supposing that, or by EA is equal to EB. So if we can prove that EA is not higher than EB, that means indirectly what we can say, EA is equal to EB. Okay, so to prove EA is equal to EB, we have to first prove that EA is not higher than EB. So for that, let's suppose EA first. Let's suppose EA is higher than EB. That means epsilon A is greater than epsilon B. Okay, that means the efficiency. Okay, so suppose QH amount of heat is absorbed by the machine A, and it will going to convert some amount of this heat into work. Okay, and the remaining part which cannot be converted by that machine, let's suppose this is your QC, which is QC, and this QC will going to be removed, or this can be go to the cold sink. Okay, again, suppose the machine B can absorb QC amount of heat from that sink, and it will going to do some work, and it will going to remove some Q dash H amount of heat into that source. Okay, so the thing is that this B will not going to actually absorb QC amount of heat from that cold sink easily. So we have to, it will going to require some amount of energy. So let's suppose that energy will coming from a part of W. Okay, so let's suppose this is your W dash. because the efficiency of, we consider that efficiency of EA is higher than the efficiency of B. That means only a part of work will be sufficient. That means all the work will not going to be used by this machine B to absorb QC amount of heat. Okay, so only a part of work will be absorbed by this you know this system B to absorb QC amount of heat. Okay, so now this is, let's suppose this is the condition. Okay, so the remaining part will be, that means this is W minus W test will be the work which will be observed from that from that whole overall process. Okay, so now if you look at the overall process, then you able to notice that here for the first case, that means for the first that means for the machine A, it will going to absorb some heat, that means QH amount of heat from that source. So as a result, the temperature of the source will going to decrease. Okay, so that means when, so first in the machine, in case of machine A, okay, so it will going to absorb QH amount of heat. Okay, it will going to absorb. Okay, absorb. So as a result, what will going to happen? As a result, the temperature of the source will going to decrease. Understand? So the temperature of the source will going to decrease first. Okay, again it will going to release some amount of heat, that means QC amount of heat to that sink, because it will not going to convert all the heat into work. Okay, it will be not possible for this machine, no? So it will going to release QC amount of heat to that cold sink. That means the temperature of the sink will be increased. Okay, so that means in case of for the same machine, the QC, excuse me, okay, QC amount of heat will going to released by that machine A to that sink. Okay, so the temperature of the sink will going to increase by how much amount? By QH amount, sorry, QC amount. Okay, QC amount, and this is Q amount. Okay, so this will going to decrease QH amount, and this will going to increase QC amount. Okay, so if you now go to the machine B, then the machine will going to absorb QC amount of heat from that sink. That means for the machine B, QC amount of heat will going to be absorbed by the machine B from sink. So from sink, that means the temperature of the sink will going to decrease how much amount? QC amount of. Okay, again it will going to release the additional, that means the extra heat, which is QH dash, to the source. Okay, so and it will going to released Q dash H, QH dash amount of heat to the source. So that means temperature of the source will going to increase how much amount of energy? QH dash. Okay, so these are actually the four changes. Okay, so QH amount of heat is absorbed by that machine A, and QC amount will going to be released by that machine A to that sink. But in case of machine B, QC amount of heat will going to absorb. Okay, so here you see this sink, in this case of the sink, in first machine, for the first machine, it will going to absorb QC amount of, not sorry, it will going to release QC amount of energy. That means the heat will going to increase. That means the temperature of the sink will going to increase how much? QC. Okay, but here for the machine B, it will the temperature of the sink will going to decrease QC amount. Okay, so that means these two will going to cancel out with each other. So that means the temperature of the sink will going to be remain same. So that means temperature will going to will be same. Okay, will going to remain same. Okay, for that cold sink. But in this case, in the case of source, that QH is actually higher than QH dash, because the efficiency of the B is okay, actually it will going to absorb more now. So actually that QH heat of QH is greater than QH dash. Okay, so that means the net effect in that source will be what? The decreasing of temperature, because here it is decreasing of temperature is by how much amount of energy? QH. Okay, and here QH dash. Okay, but QH dash is less than QH, so the temperature will going to decrease. So that means the temperature, the net temperature of this one will going to decrease. Okay, it will going to decrease. Understand? So but here it will going to, it will be same, and here it will be decreasing. But is it true? Is it possible? No, it is not possible, because according to the second law of thermodynamics, we know that, because let's suppose this is a system, okay, and this is the surrounding. So if the temperature of this system is increasing, okay, then the surrounding must be decreasing. That means some amount of heat will going to be absorbed from that surrounding, okay, to increase that temperature of the system. Okay, so the surrounding temperature will going to decrease. Okay, so that means this concept is wrong, because here you see the temperature is decreased, but here it will be same. So it will be not same. If it is decreased, then it should be increased. If the temperature of the source will going to decrease, then the temperature of the cold sink should be increased in the same amount of, okay, to to actually satisfy the second law of thermodynamics. So that means what we can say, that EA is not equal or is not higher than EB. That means the efficiency of the machine A is not the efficiency of the machine B. If it is like this one, then the second law is violated by this whole system. Okay, the whole system, overall system. Okay, so since this is not correct, so we can say that EA is equal to EB. That means the efficiency of the machine A is equal to the machine B. Understand? That means what we can say, the efficiency of a machine A and the efficiency of a machine B is always equal if we put them in the same, in between the same source and same sink, regardless of the substance which are used to prepare this two substance. Understands? And since actually the or in another words, what we can say, this this experiment, this theoretical experiment follows that the relation between the heat transfer, okay, the relation between the heat transfer and the temperature must also be independent of the working materials. That means the materials which is used to prepare this to machine, and therefore we can say that this integration, cyclic integration of ds is equal to 0 is always true for any substance involved in a Carnot cycle. Okay, so I think you understand this point. That means we have already proved that the entropy is a state functions for any substance okay, for any substances or for any working materials, okay, or for any substance involved in a Carnot cycle. So the second point is proved. Okay, so now we're going to discuss the third point, which is the entropy is a state functions for any cycle. Okay, so let us discuss this one. So coming to the third point, which is the entropy is a state function for all the cycles. Okay, so we can use this you know the a cycle. Let's suppose this is your cycle, and this cycle can be composed of many infinitesimal cycles, or we can say that any reversible cycle. Say suppose this is a reversible cycle, this is, let's suppose this is initial point, and we can get that initial point after completing that cycle. Okay, so suppose this cycle can be this cycle is first of this should be irreversible cycle. Okay, a reversible cycle, and this cycle can be represented as a collection of many cycles, many Carnot cycles. Okay, these are the many cycles, many Carnot cycles. So this is one cycle, this is one Carnot cycle, let's suppose this is also one Carnot cycle. Okay, so it can be represented by many cycles. So even we can represent a very very small cycles. Okay, small infinitesimal collections of the what your Carnot cycles, and then the cyclic integral around an arbitrary path is the sum of integrals around each of the Carnot cycles. That means that the cyclic integrations, that means the cyclic integration of ds around the arbitrary path, that means this part, this all part is actually the sorry, the sum of the integration around the actually the sum of integration around the each of the Carnot cycles present in that in that area. Understand? So we again know that it is already proved in the first point that the change of entropy for the cyclic process, that means cyclic integration ds is equal to 0 for Carnot cycles. That means the d, that it means integrations of integrations of, that means you can say that integration of ds is equal to 0 for one Carnot cycle. Okay, for this Carnot cycle it is 0. Similarly for this one also it will be 0, that means that integration is 0. For this one also that integration is 0. So if you sum up all the that if you sum up, that means summation of that dq reversible by t, or you can say that ds, all the cyclic integration, if you sum up all the cyclic integrations like this one, then the overall because this represent, this will be 0, this will be 0, this will be 0, this will be 0. So every Carnot cycle will going to have what, this value, 0 value. So that means if you going to sum up the integral around each of the Carnot cycles, then the total summation will also be equal to 0. That means we can say that the entropy is a state function. That means the integration, cyclic integration ds is equal to 0 for the arbitrary path. That means this path, this cycle. Okay, this cycle, for this cycle also the integration will be 0. Hence we can say that the entropy is a state function for any cycle, Okay, understand? Hope you understand this point. So now so we have already proved all the 3 points. That means the first point is your ds is equal to what, the first point is your integration ds, that means cyclic integration ds is equal to 0 for any cycle. So not for any cycle, for Carnot cycle, Carnot cycle. This one is already proved. The second point is the entropy is a state function for any substances. So we have proved this one by using the concept of efficiency. And third one is also proved by using the arbitrary path. And we consider that the arbitrary cycle, that means the path is composed of many infinitesimally small Carnot cycles. Okay, so these three are already proved. So that means what we can say? We can say that the entropy is a state function for all the macroscopic systems or all the macroscopic substances. Okay, so we can use this concept for all the macroscopic systems. That means it is universally true statements. Okay,